Right. This is the second part of our sequencing lesson, lesson 26. And for this lesson, we're going to be talking about sequencing jobs through two sequential processes, just to follow on what we've done previously. All right. There's still going to be several sequencing orders that are available. Again, any of these that we saw previously are still available. First come, first served, shortest processing, longest processing, due dates, any of those are still available and help us sequence these jobs. But before we go into the specific sequencing, I want to talk about how this is going to work. All right, so we're first starting out. We're going to assume that this is a first come first served sequence, that we're going to serve A, B, C, D, E, first come first served. All right, first come first served. All right, as they go through these two processes, and here's process one, process two. Again, their order is going to be A first, and then A first, and then B, and then C, and then D, and then the E. So this is still the sequence as we move through the processes from left to right. All right, so when we start working on this set of jobs, of course, we take A off of the line and we move A into our first process. It completes its work based on its job duration. Then as soon as it is completed, it moves over and begins work on process two, because process two is available. There's no other job there, and so A can start immediately. And then also our job B, we take job B off, and we put job B can start on process one as soon as A is complete. All right. So now then we have our situation that's shown here. We have process A that's in progress on process two. We have job B that's in progress on process one. Now, one of the things that's it can be confusing for students about this situation is now there's two things that can happen. The first thing that can happen is, I guess, the easier thing. If job A finishes first and it moves out of these processes, then process two becomes idle until process B finishes on process one. But then once process B is finished here, it can move over and begin immediately on process two. And then of course we'll take C off of the out of the link, and C will begin to work on process one. Okay, so that's the first thing that can happen. And this is the case where A finishes first on process two. All right, but there is another thing in our situation here. There's another thing that could happen, and that occurs when B finishes first. And if B finishes first and A has not already finished on process two, then what happens to B? Well, job B goes over to process two, and it waits. B waits until A is finished. And as soon as B finishes here, it begins waiting on process two, and then we'll take job C off the list, and job C can begin to work go to process 1 immediately while B waits. And then job B waits here until A finishes. And then as soon as A finishes and moves on, then B can begin and ends its waiting. And in fact, there could be multiple jobs waiting on on process 2, if depending on how long it takes to process to complete jobs on process 2. So that's the second thing that could happen. Let me erase this. The second thing that can happen is when if B finishes first and goes over to process 2 and waits for A to finish on process 2. Hopefully that makes sense. And I think as we look at an example, will make it a little bit more clear here in a minute. The other thing is that there are, because there's 2 processing times, that gives us the opportunity for other job sequencing options. So the first thing that I want to point out here, and again, our example, we're going to have 5 jobs still. And again, that gives us 5 factorial possible sequences, or 100, we know that's 120. And the way the data is organized, even though the table looks the same, you're given the processing time for each job. So the processing time for A on process 1 is 6 days, and it's 8 on process 2. So this table is processing times, not processing time and due date. Now, because we have 2 processing times, it gives us the option for several other sequences. And one that I want to look at is the shortest processing time on process 1. And the shortest processing time on process 1 will just look just with respect to these processing times and sequence them in the order of the shortest. And we know which is the shortest. E is the shortest at 5, and then A with 6, and then C with 7, and then D with 9, and finally B. So E, A, C, D, B is that sequence with respect to the shortest processing time on process 1. Then similarly, we could choose the shortest processing time on process 2. So we just look with respect to the processing times on 2, and we'll notice that C is the shortest, and then B is next with 6, then D is next at 7, A is at 8, and then E at 10. So C, B, D, A, E is that sequence for the shortest processing time on process 2. And then similarly, you could just look at the longest processing times on either process 1 or process 2. And then there's one other that I want to explain, and that's where we would calculate. First of all, we would calculate the total shortest processing time on both machines. So we're going to look at, first of all, the total processing times on both processes. And so what this does is we're going to take the processing times for A, which is 6 and 8, and of course that's 14. The total processing time for B is 11 and 6, 17. For C, you can see is 7 and 3 is 10. For D is 16, and for E is 15. And just like before, now we've got the total processing time. and we're going to choose to use the shortest total processing time. And again, the first one in the sequence will be C. Then we're going to choose A at 14, and then E at 15, D at 16, and then B. So that gives us the sequence CA, E, D, B. And again, you could look at the total longest processing time, or you could have other rules of thumb or other heuristics. The one that we're going to look at most closely, though, is the rule that's called the Johnson's rule. And Johnson's rule, again, you'll see the Johnson's rule explained on page 750 to 752. Johnson's rule guarantees the minimum make span. And I want you to remember what the minimum, what make span is. Again, just as a refresher, the make span is the total time it takes to process all jobs through both processes. So the key thing is to remember the Johnson rule guarantees the minimum make span. It doesn't guarantee it'll give you the minimum tardiness or the maximum number of jobs completed on time. Only the minimum make span. All right. And so let's see how this works in an example, how Johnson's rule works. Okay, it gives Johnson's rule, again, gives the fastest way to process a series of jobs through a two-step system when all jobs follow the same process. So here's how this works. The first thing that we're going to do is from among all of the processing times, we're going to find the smallest processing time. And in this case, the smallest processing time is this corresponds with job C. All right, and because this occurs on our second process, we're going to place job C into the sequence, into the spot that's the last spot or the farthest spot near the end. And so this is going to be job C. All right, now we continue that. What's the next shortest process from this table? And you will see there's a 5 is the next shortest process, and that's job E. But this this processing time occurs on the first process. And so we're going to take now job E, and because it's on the first process, we're going to place it as near to the front of the order as possible. And then we continue. So we've taken C out, we've placed C and E. So from among the remaining, D, A, and B, what is the shortest processing time? Well, we have a tie. 6 on A and 6 on B are the next shortest. And we can break the tie arbitrarily, and so we're just going to look at B first. This occurs on B's shortest processing time occurs on process 2. So now we're going to put B as near to the end of our sequence as possible, back in position 4. And we're going to take B out of the rotation. And then finally, we're going to look at A. A, that's shortest processing time, occurs on process 1. So job A goes to the nearest, farthest to the front as possible, to the earliest as possible. And then, of course, that leaves only one job left to place, which is job D. And so this is our sequence based on Johnson's rule. And again, we're going to translate this down. So the sequence based on Johnson's rule is E, A, D, B, and C. E, A, D, B, C. Now, the next thing that we're going to do is we're going to take our processing times and we're going to put them in our table. And notice, let me clear this out. Let me leave this like this a little bit. We're going to put our processing times with respect into each one of these durations, into the duration column, I should say, for process 1 and process 2. And so for E, its processing time on job 1 is 5. Its processing time on job 2 is 10. For A, it's 6 and 8. For D, it's 9 on process 1 and 7 on process 2. For B, it's 11 on process 1 and 6 on process 2. And for C, it's 7 on process 1 and 3 on process 2. Let's double check and make sure. E, 5 and 10. A, 6 and 8. D, 9 and 7. B, 11 and 6. C, 7 and 3. Okay? So now we're going to start, and we're going to actually do the calculations on following through. So for job E, again, it's going to start at time 0. We'll start the clock at time 0. We start at 0. It takes 5. We're going to finish at time 5. And again, we can go directly and we can start at time 5 on process 2, and we'll finish with job E at time 15. Now you'll notice, again, I'll point out there's no durations, there's no due dates out here, so we're not, at this point, we're not calculating any tardiness or any jobs that are late. We're just calculating the finishing times. All right. Notice now, that when job E finishes on on process 1, job A can begin immediately. So job A begins at time 5, and it'll finish at time 11. And again, these are plus. We're just doing the arithmetic. Now for job A, process 2, notice that job E is not finished. So job A cannot start at time 11, but it can only start at time 15. on process 2. And if it starts at 15, it'll finish at time 18. 15 and 8 is 23. Now back to process 1 and job D. It can start right at 11. It finishes at time 20. But again, process 2 is still busy at time 23. So job D cannot start until job A finishes, which is at time 23. And it'll finish at time 30. Job B can begin as soon as job D finishes, so it can start at time 20, but it'll finish at time 31. Now be careful here. What time can job B start on process 2? Well, we're going to compare these two numbers, 30 and 31. This is kind of like, in a way, a lot of like our critical path work that we did. It's going to be, it will be the maximum of those two values. And so job B can't start on process 2 until it finishes process 1 and when process 2 is available. So this is going to job D start at time 31 and it finishes at time 37. Job C starts at time 31. It finishes at time 38. And similarly, it can start process 2 at time 38 and will finish at time 41. So there's things that I want to point out here. Again, our make span is 41. This is our make span. And what I want to say is that will be 41 is the minimum make span for these sequence of jobs from among all of our 120 jobs, 120 sequences. The make span will never be less than 41. Now that doesn't mean there might be other criteria that this is worse than, but again, from among all of the 120, and there may be some others that have 41 make span, but there will be none less than 41. Okay, hopefully that makes hopefully follow through. Again, follow through this example and make sure that we understand how to compute the processing of jobs through two processes. Again, I'll leave that to you to try again. Again, the whole key is to build this Johnson's rule, to use the Johnson's rule appropriately. And again, this is a cleaner version of our sequencing, and you hopefully would be able to follow through again with the solution. And finally, here's Johnson's rule. Again, it's just what we've said before. Just you list the time required to process each job at each machine. Set up a one-dimensional matrix with respect to represent the desired sequence with the number of slots equal to number of jobs. What does that mean? That was our, as you saw, that was our horizontal matrix on the previous, and we had five different cells 1, 2, 3, 4, 5 for the jobs that we wanted to sequence. That's the one-dimensional matrix. Select the smallest processing time on either machine. If that's on machine 1, put the job as near to the beginning of the sequence as possible. If it occurs on machine 2, put the job as near to the end of the sequence as possible. Remove the job from the list. Repeat those steps until all slots in the matrix are filled, and that produces your sequence. Okay, that completes that. Good luck. Practice this. I would say go back and practice this. Again, you can print this slide. I would practice this with various sequences to make sure you understand. All right. Good luck as always. Call me, email me, text me if you have questions.